The famous mathematician David Hilbert once said, "The art of doing mathematics consists in finding that special case which contains all the germs of generality." What he meant by this is that the mathematician's ultimate goal is finding truths that apply to the most general of cases. But deep down in mathematics, there lurks a little greedy gremlin striving to counter these efforts. For every little bit of generality you try to gain, he takes away something you had before. This tug of war is present in all mathematical disciplines. Here, we are going to look at one of the negotiations with the greedy gremlin on the topic of fixed point theory. But this isn't just the story of different fixed point theorems, but rather the story of the relation between different theorems and what one sometimes has to give up in order to get a more general result. But what even is a fixed point? Take, for example, the function f of x is x squared. Now, a point we call a fixed point if f doesn't change it, if the point stays fixed. So a point x0 we call a fixed point of f if f of x0 is again x0. This means that 1, for example, is a fixed point of f, since f of 1 is the square of 1, which is, again, 1. But 2, for example, isn't a fixed point, because f of 2 is the square of 2, which is 4, so not again 2. The function f of x is x squared has one more fixed point. Can you find it? You could just try a couple of numbers. Anyway, some functions don't have a real number as a fixed point, like the function f of x is x squared plus 1. Since apparently some functions have fixed points and others don't, this raises the question: what is the difference in nature between functions with or without fixed points? Answering this question for the most general cases is our goal that the greedy gremlin tries to sabotage. Finding fixed points is not only something interesting in itself, but it is used in many applications, such as the field of partial differential equations, which describes the world around us and how it works, and also it is used in the field of optimization. Most of the time, we aren't only interested in finding fixed points of simple functions like the ones we had before. A function is just something that takes one object and assigns it to another object. So for example, the function that assigns to every married person their spouse is also a function in a mathematical sense. And it has no fixed points, since nobody is married to themselves. On the other hand, the function that assigns to every person the person that knows them best is a function that has a lot of fixed points, since most people know themselves best. So if you know yourself best, you're a fixed point of this function. In case you know a little bit of calculus, here's another weird function. Take the function that assigns to every function its derivative. Then the exponential function is a fixed point of this function, since the derivative of the exponential function is again the exponential function. The takeaway here is that the concept of functions doesn't only work on numbers, and neither does the concept of fixed points. Since we are interested in finding fixed points, it might be handy to find properties of functions that already guarantee that this function has a fixed point. Let's start simple. Let's take a set, including its boundary, and this set should be bounded, so not infinitely big. And then we want one more thing, namely that the set is convex, which means that for any 2 points of the set we choose, the connecting line should stay within the set. Now imagine we have a function on this set. It just moves every point of the set to a different place. If this function does this without ripping or tearing the set, we say that the function is continuous. I've put some markings on the fabric such that we can see how the function moves the set better. If the function is continuous and it's defined on such a set, then Brouwer's fixed point theorem tells us that this function has at least one point that stays the same. It is a fixed point. Brouwer's fixed point theorem is really neat, but it only works in the plane, or in space, or actually any finite dimensional set. But what should infinite dimensional sets even be? We'll find out right away, but for me, first it's time for a coffee break. By the way, stirring coffee in a cup is also a continuous function. So Brouwer's fixed point theorem guarantees that no matter how much you mix, there will always be some molecule in the coffee at the same spot as it was before mixing. I said before that Brouwer's fixed point theorem only works for finite dimensions. However, we would like to generalize it to work for infinite dimensions too. But what do we mean by a dimension of a space? Usually, by the dimension of a space, we mean the number of values or coordinates we need in order to describe a point of the space accurately. So if the space is a line, we need one coordinate in order to describe any point on the line. If the coordinate is 5, we just measure the distance 5 from 0, and this is our point. If instead of the line, we take the plane, we need to add one more coordinate axis. And every point can be given by its distance in this direction from 0 and its distance in this direction from 0. And if instead of the plane we went the whole space, we need one more coordinate axis. So what does infinite dimensional mean then? Do we just add infinitely many coordinate axes? No, a porcupine isn't infinite dimensional. Infinite dimensional sets are a little bit more sophisticated than that. Take, for example, a set of all functions from the real numbers to the real numbers. Every such function can be represented by its graph. We can draw that here. The function may do anything. It can even jump. So how many values do we need in order to describe this function accurately? Well, we need to specify its value at 1. That's one value. Then we need to specify its value at 2, and also at 3, and so on. But then all the numbers in between, we also have to say what the value is, like at 2.5. You see where this is going? We need infinitely many values in order to describe this function accurately. Defining a function on an infinite dimensional set, like a set of functions, really isn't too far-fetched. Remember, we already had the derivative function, which takes as an argument a function and assigns to it its derivative. So defining functions on infinite dimensional sets really isn't too uncommon. And this tells us that we need a fixed point theorem that also works in infinite dimensions. The Banach fixed point theorem is exactly what we need here. And the idea is really simple. We don't have to think about infinite dimensional things at all. Take a function that makes distances smaller. What I mean by that is that we have a function that for any 2 points we choose if we compare their distance to the distance of the points they are assigned to, these points are now closer together than the original ones were. By decreasing distances, the function shrinks everything together. If we take any interval and we apply the function to it, then it will shrink it. If we apply it again, it will shrink it again. If we do this over and over and over, everything gets shrunk until, essentially, nothing changes. You've reached the fixed point. Let's describe these shrinking functions more accurately. If we know that there is some given percentage by which distances are shrunk at least, say 30%, then we call such a function a Lipschitz contraction. It contracts everything together. Formally, this means that there is a positive constant L less than 1, such that for all points x and y, we have that the distance between their function values is less than or equal to this constant times the original distance. Let me repeat this since it's really important for us. A function is a Lipschitz contraction if there is some number L less than 1, such that if we take any 2 points and compare their distance to the distance of the points they are assigned to, we know that the distance shrinks at least proportionally by the factor L. These functions are important for us because the Banach fixed point theorem tells us that all Lipschitz contractions have exactly one fixed point. I'm here at the confluence of the 2 rivers here in Innsbruck, Austria. This is the river Inn, and this is the river Sill. I'm here because their meeting point can be easily identified on a map. I have a map of the region here, and the map has a scale. And the scale tells us by what factor distances from reality are shrunk in order to fit on the map. This means that this function that takes every point in reality and assigns it to a point on the map is a Lipschitz contraction. In that case, what is the fixed point of this Lipschitz contraction? Well, it can't be a point far away because the point is assigned not to itself, but to a point over here on the map. By this logic, the point where I'm standing right now, the point where the 2 rivers meet, this must be the fixed point of the Lipschitz contraction. This point is right above the point where it is in reality. In this case, it was clear that the function shrinks distances. Sometimes this is harder to see, and a different perspective on Lipschitz contractions can be helpful. If I draw some function here, how can I tell if it's a Lipschitz contraction or not? If I take any 2 points and look what values the function assigns to them, then this has to be closer together. So for every horizontal distance, the vertical distance must be smaller. If L is 1/2, then the distance must be at most half of what it was before. So if the function were really steep, then this wouldn't work. The constant L tells us that the steepness of the function anywhere can't be more than the steepness of a line with slope L. The function has to stay below this line, no matter what point the line starts at. So remember that a Lipschitz contraction has a maximal overall steepness of L. We'll get back to this later. Now for the next bit, we'll need a little bit more sand. So let's go upstream a bit. Up until now, we had 2 fixed point theorems. Brouwer's fixed point theorem, which works for continuous functions, but only on finite dimensional sets. And then we had the Banach fixed point theorem, which works on infinite dimensional sets, but only for Lipschitz contractions. So by demanding a result that works on infinite dimensional sets, The greedy gremlin stole away any statement about fixed points of continuous functions that aren't Lipschitz contractions. But we aren't ready to give up yet. Can we maybe find a way to trick him into giving us more functions? Well, we know something about Lipschitz contractions, but not all functions make distances smaller. What if we try to formulate a similar theorem to the Banach fixed point theorem, but for functions that don't only make distances smaller, but also may leave them the same? Such functions we call non-expansive functions, since they don't expand distances, but may shrink them. An example of such a function is a simple shift. If we take the real line and we take any two numbers and just shift them, then their distance stays the same. But this function doesn't have any fixed point, since all points shift. So this is a problem. Apparently, the greedy gremlin doesn't allow us to formulate a fixed point theorem for all non-expansive functions. Maybe though, we could sneakily steal back at least almost all of the non-expansive functions. But what should almost all even mean? Like 99% of functions? This is weird and also way too difficult to compute. Instead, we are going to use something called porosity. Porosity is something that is similar to a sponge. A sponge has a lot of holes, a lot of air, almost just consisting of air. The sponge itself is almost nothing, and the air is almost everything. And this concept also works for sets, such as the set of non-expansive functions. Take, for instance, the filled circle. If we take a hole away in the circle, then there is less of the circle left. And if we take away another circle, then there is even less of the circle left. If we take away more and more and more holes, essentially, there will be no sand left. The holes make up almost everything, and the sand is almost nothing. We can formalize this idea. Let's choose any point of the small set. Now here we can see that no matter how close we go to this point, I'll mark how close we want to be by the circle here. There is still a hole within the circle. Now if the size of the outer circle and the size of the hole we can choose depend linearly on each other, then we can say that the set is porous in this point. And if this works for every point of the set, we call the set porous. The linear dependence between the outer circle and the hole gives us control of how big the holes are. Sometimes these two don't depend linearly on each other, but that's okay too. It's just a weaker version of porosity. So a porous set is a small set, and the holes themselves are a big set. Such a big set we call a coporous set. One more thing we can do is take unions of such small sets and still call them small. So if we take a countable union of porous sets, we still think it to be a small set, and we say that such a set is a sigma porous subset. Everything except for this set we consider a big set, a co-sigma porous set. Don't disturb my circles! Sorry! The problem we had before was that not all non-expansive functions have a fixed point. But we would like to show that almost all non-expansive functions have a fixed point. This means we want to show that the functions with a fixed point are a big subset, a co-sigma porous subset. But in order to do this, we need a notion of holes or circles. So circles with the center being a function. In order to do this, we need to be able to measure distances between functions, since a circle is all points that are at most the radius far away from the center. How do we measure distances between functions? There isn't only one way to do this, but we're going to look at one possibility. So if we draw two functions here, we just need to look for where they are apart most and call this the distance of the functions. Since we want holes, which are circles, we could think about what a circle with some radius around this function would look like. A circle with some radius r is just all points that are at most r far away from the center. Here the center is the function. So the circle around this function would consist of all functions that differ everywhere at most r from the function f. This is easy to draw. We just draw a tube around f with radius r. Then, every function that can be drawn inside this tube is inside the circle around f. A weird way of thinking about circles, but it works for functions. Now, using this way of measuring distances, we are able to use the idea of porosity within a set of functions. Since the greedy gremlin stole away the non-expansive functions, we can now use porosity to trick him into giving us back almost all non-expansive functions. De Blasi and Miak did some research in this direction. They were able to show the following result. Almost all non-expansive functions have a fixed point. In other words, the functions that have a fixed point form a big subset of the non-expansive functions, a co-sigma porous subset. Now you might ask, why is this the case? Is this maybe because already most of the non-expansive functions are Lipschitz contractions? Since Lipschitz contractions are non-expansive, they don't make distances bigger, and all of them have fixed points. As it turns out, this isn't the case because de Blasi and Miak also showed that there are almost no Lipschitz contractions within the set of non-expansive functions. So what functions then make up these many good functions with a fixed point? It turns out most of these non-expansive functions are Rakotch contractions. Rakotch contractions are very similar to Lipschitz contractions in that they make distances smaller, but they don't do this by at least some factor. Instead, this factor may depend on the distance of the original points. Remember from before, we said that a function is a Lipschitz contraction if it stays below this line, no matter where the line is. Since L is less than 1, the line is always less steep than diagonally. Now for Rakotch contractions, instead of the line, we can use any other random curve that stays below the diagonal. This still describes a function that makes distances smaller. We will use this way of thinking of Rakotch contractions later. By demanding a result that works for non-expansive functions, the greedy gremlin stole away almost all Lipschitz contractions. Even though the greedy gremlin did its best at countering us, victory is ours for the most part. The takeaway here is that even in mathematics, you can't have everything. And sometimes you have to give up one thing in order to get something else. You can't escape this trade-off. And to give up as little as possible, the concept of almost all can sometimes be very helpful. I hope you've enjoyed the video and learned something new. The rest is somewhat a bonus part, so feel free to just stop watching here. It doesn't really give you more insight into the nature of the greedy gremlin, but in case you still haven't heard enough about fixed point theorems, we will go through one more brand new theorem that was only published this year and co-authored by myself. Also, we are going to look at part of its proof. So it seems we have solved the entire fixed point problem for non-expansive functions in infinite dimensions. We know that almost all non-expansive functions have a fixed point, and this is because almost all of them are Rakotch contractions. But up until now, we only know this on bounded sets and not on infinitely big sets. What happens there, we don't really know at all yet. If we want to talk about non-expansive functions on unbounded sets, we again need a way of measuring their distances. The metric we used before on bounded sets is a bit too restrictive for our case, since it limits how far apart functions can be everywhere, up to infinity. Instead, we use a different metric. But this can be easier seen if we take a look at functions that map points from the plane to some height. Then this pile of sand could be such a function. When we want to measure distances between such functions, we use a similar method as before. But instead of looking at the maximal difference everywhere, we limit this to circles with integer radii. If I change the function here a little bit, then we get a new function. The way we measure the distance is that we look for the maximal difference between this function and the original function on every one of the circles, and weigh it with the powers of 1 over 2. So in the first circle we have no difference, and the second one neither. In the third we have a difference, and we weigh it by 1 over 2 to the third, so 1/8. In the next we weigh it by 1/16, and in the next we weigh the maximal difference by 1/32, and so on. So if dn of f and g tells us the maximal difference between the two functions on the circle with radius n, then we write down the distance of f and g as d of f and g is 1/2 times d1 of f and g plus 1/4 times d2 of f and g plus 1/8 times d3 of f and g, and so on. Now a nice thing about the weights 1/2, 1/4, and so on is that they sum up to 1. And in order to keep this for the metric, we instead of d1 of f and g use the term d1 of f and g over d1 of f and g plus 1. And the same at all the other places. This way, the part where the metric occurs is smaller than 1, and the whole sum also stays smaller than 1. Let's say that d1 of f and g were 1,000,000. Then the fraction would essentially be 1,000,000 over 1,000,000, so basically 1. This tells us that no matter how far the functions are apart, the fraction stays below 1. All in all, we use this metric. Since we weigh the differences in every circle by 1 over the powers of 2, which is a very fast decreasing sequence, we can see that the metric cares a lot more about what happens close to the origin than what happens far away. In other words, the metric is short-sighted and sees the function more like this. Okay, let's go back to the actual fixed point problem. When we defined our functions on bounded sets, we said that almost all of them are Rackhotch contractions. And since they all have fixed points, we said that almost all non-expansive functions have fixed points. Now one could hope that this also works for the unbounded case. But the greedy gremlin learned from our strategy of using almost all, and now he took back almost all Rackhotch contractions, meaning that there are almost none left. Realizing this is actually a completely new result, only published this year by Bargetz, Reich, and myself. Although I should mention that Strobin already found this in a related case. In short, we showed that on an unbounded set, there are almost no Rackhotch contractions. The set of Rackhotch contractions is a very small subset. Apparently, changing the set changes the whole situation. But why is this the case? We are going to prove that the set of Rackhotch contractions is a small subset, a sigma porous subset. So the sigma part tells us that we need to write the Rackhotch contractions as the union of some sets R1, union R2, union R3, and so on. And then we need to show that every one of these sets is porous. Let's choose one, say R1. In order to show that R1 is porous, we need to prove that for any function in R1 we can choose, there is another function g close to this function f, which doesn't belong to the set R1 anymore. And also, we need to show that around g there is some circle that completely stays outside of R1. So how do we do this? It sounds incredibly complicated. Remember The Rackhot contractions were all functions where we can bound the steepness by these weird bounding curves. Now if we draw all of these random curves, we have a huge mess. Proving anything about a mess like this seems impossible. We tackle this problem the same way we tackle difficult problems in real life. We separate the mess into a lot of little messes and deal with each one separately. For example, we can just choose a point and take only the curves that go below this point, or below the red line equivalently. Now if we choose a lot of these points and count through them, like first point, second point, third point, we are able to fill the entire region below the diagonal. This gives us a way of choosing countably many messes, and each mess describes a set of Rackhot contractions. That is, all functions where the steepness bounding curves go below this red point. Okay, let's take one of these steepness bounding curves and choose a function that stays below it. What we have to check is if in every point the function really stays below this bounding curve. If it does this for every point, then we know that the function belongs to R1. Now in order to find a hole, we need to find a function g close to f such that it can't belong to R1 anymore. How do we do this? If we make the function steep enough, then it can't belong to R1 anymore. But how do we ensure that this steeper function is close to f? Well, if we made it steep, say here, then it would be far away from f, since the inner circles are far more important than what happens far away. This tells us that we can use that our metric is short-sighted, and therefore just make the function steep somewhere far away. Now to make the function steeper far away, we first make it steeper just a little bit to build a platform on which we can then put a really steep tent-like structure. So here is the platform, and then we put this on there, and now the entire function is way too steep here to belong to R1. We can see this since the bounding curve of R1 just won't bound the function now. This means we have found the center of our hole. All that remains is arguing that all functions that are really, really close to the center are still too steep to belong to R1. In other words, we have found a hole. And since f was completely arbitrary, the same works for every other function f within R1. This means the set R1 is porous. The same idea works for every other set, R2, R3, and so on. This means we have shown the set of all Rackhot contractions is sigma porous, so a small subset. There are almost no Rackhot contractions. Does this now mean that almost no non-expansive functions have fixed points, since almost none of them are Rackhot contractions? No, it doesn't. Also, other functions can have fixed points. And this is our angle at getting back at the greedy gremlin. He might have taken away almost all Rackhot contractions, but there still may be other functions that have a fixed point. So then, do almost all non-expansive functions have a fixed point? In our research, it turned out that yes, almost all non-expansive functions have a fixed point. But this is due to a slightly different reason. It's not that almost all functions are Rackhot contractions, but that almost all functions are Rackhot contractions on bounded sets. Since any unbounded set contains bounded sets, this means that almost all functions have a fixed point. Proving this, though, will go beyond the scope of this video. So you'll just have to trust me on that. Also, I should mention that Reich and Zaslavsky already showed this for a related case. Now what we've learned is that on an unbounded set, almost all non-expansive functions have a fixed point. In contrast to the case where the set is bounded, this isn't because almost all non-expansive functions are Rakoč contractions, but rather because almost all functions have a bounded set which is mapped into itself, and on this set the function is a Rakoč contraction, so it has a fixed point.